So off we go. I want to introduce this by saying what our goal is. How are we going to evaluate how good a screening test is? You already done some of that yesterday in your calculations. So we're going to use today a mammogram, which is a test to screen for breast cancer. And here are the new assumptions. So they're a little bit different than the assumptions that you dealt with yesterday. So the probability of breast cancer at any point in time is 1%. Women who don't know they have breast cancer, but the mammogram is a test that can show it early before it has a chance to do its mischief. And so these numbers come from the 1970s when I started practice and had at Martinez and had to deal with these issues. So then it was 90% sensitive and 90% specific. It may be different today. It is different today. But I think this exercise is going to illustrate some points that you were getting at yesterday when you were studying COVID. So today we're going to look at conditional probability. What if a woman has a positive mammogram? And that's a very disturbing possibility for women. What's the chance they actually have a positive result? Analyzing this, only 3% of practicing physicians could answer this correctly. And quite often they missed spectacularly, way off base. And it's because the concepts are hard to grasp. They're abstract. And what we're going to use to clarify this, of course, is what I was taught was the 2x2 table in medical school. No further explanation. This is the 2x2 table, and you dealt with this yesterday. You calculated the sensitivity of the COVID test and the specificity. And here we're going to look at the test results in the real world. If the test is positive, what's the likelihood that it's really a true positive? Or what if it's a false alarm, which means that patients will have worried unnecessarily? And the negative test is what's the likelihood that the person really doesn't have the disease if it's a negative test? And so you did this yesterday, just to review. You calculated the sensitivities, and it was 95%. And the higher the sensitivity, the less the false negatives. No test is perfect. No test is perfect. So there's going to be some cases of COVID that the test misses. And similarly, on the other side, you calculated the specificity, and you found that it was pretty darn good, right? 98%. That's impressive. And so what you want to do is minimize the false positives, right? Because you don't want false alarms. Just like with the negative test, you don't want false reassurance, and no test is positive, so every test is going to have some false alarms. And so what I've done with these numbers is adjust the size of the cell to accommodate the true numbers. And you see we've got it color-coded for the imperfections of a test. Here are the false negatives, unavoidable. No test is perfect. And here are the false positives. No test is perfect. And you can see the new numbers today that we're going to use for the mammogram that was in the initial assumption. 90% sensitivity, 90% specificity. Now, in this model, there are three lines: one line, two lines, and there's a third line, and there's a third line in the middle. And we're going to play with this line in just a second as we deal with prevalence and how prevalent the disease is. Remember, we said it's 1% of the women that have the positive, that actually have cancer. And so that's the prevalence we're working with, and how we're going to try to demonstrate to you in many different ways how important that 1% is in calculating the accuracy, the trueness of a initial positive report. So I'm turning it back over to you, Mr. Lee.
All right, Dad, can you show the next little bit that's underneath there? Let's see, is there one more? Yeah. Oh, actually, go back. We'll show that later. Okay, so if everybody could take a look at the resource page, the one that we were using yesterday. So on the back, there's a first question. We'll give you like 5 minutes to work on that. What you're doing is basically calculating the percentage likelihood of a false positive, a false negative, a true positive, and a true negative of a mammogram test, but using the three assumptions that we had. So read it. 1 second while this pops up. All right, so the next thing I wanted to take a look at, and my dad's going to explain right now. So probability trees are great, okay, but they lose some of the visual meaning. Area models are nice because they change the sizes of the boxes, and you can kind of see actually how big the pieces are. There's a visual aspect to it, almost kind of like a graph would have. So my dad's going to explain his idea about how to visualize this for doctors and get them to understand a little bit better how the conditional probabilities change when we're trying to decide how good is this test actually. So Dad, you're going to show the students next how the lines can become a little bit more dynamic. Go ahead and go to the next slide.
Okay, are you ready for me to talk?
Yes.
Okay, so here we are. We're back at this diagram. You remember we've adjusted the boxes to accommodate sensitivity and specificity, these two lines. The third line right here in the middle, this is going to be our prevalence line. And the way things stand right now is the probability that the patient that's in front of me has the disease, in my mind, is 50-50, a toss-up. But it's not always like that, right? In my mind, when I'm seeing a patient, the pre-test probability varies based on the history, the physical, what's going on in the community, as we'll talk about later. So let's make this line dynamic. Let's make it movable. What if I'm thinking, oh, I think there's only a 25% chance that this patient has the disease, 75 not. So look what happens to the relative size of two of the boxes. I'll just focus on two of them now. I'll go back. Just fix in your mind how big the yellow box is compared to the big true positive blue box. So the yellow's the false positive. They're both positive tests. So the yellow versus the blue. Watch what happens to the relative size. Boom.
Okay,
What happened?
So anybody want to think about what happened and talk to your teammates real quick and decide if we moves it even further to the left, what's going to happen between the size of the blue and the yellow? Talk to your teammates real quick. Who can tell us, give us a prediction. What's going to happen between the blue and the yellow? Owen.
It's like the blue shrinks, the yellow can get like longer.
Okay. All right, good. So think about what those, we'll talk about it in a second. You don't have to answer this quite yet, but think about what those represent. True positives versus false positives. Go ahead, Dad.
Okay, now this is dealing with a patient who has symptoms. We're talking about a 25% chance of disease, a 50% chance. But what if we go to screening? That's what this is all about. You got it with the basic data on the first slide, what the assumptions were. The assumption was that the prevalence disease for screening purposes is 1%. So I'm not dealing with a sick patient. I'm not dealing with a woman that has a breast lump. I'm dealing with a woman that thinks her breasts are fine and that there's no problem whatsoever. So that's 1%. Now, let's watch what happens to the relative size of the yellow versus the blue. Boom. Boom. What happened?
What happened, Walter?
Well, the yellow box got closer and now bigger than the blue box.
Okay, and what do you think that means?
That means that, like, for example, if you were to get a positive result on a test, it's more likely for it to be a false positive than for it to actually even be the actual positive test because it's a higher chance.
Correct. So this is what we're going to calculate right now. So Walter just said it means that now that the blue box is smaller than the yellow box, it's actually more of a chance it's going to be a false positive than actually a true positive. So go ahead and go to the next slide, Dad.
Okay, before we leave, I just want to point out that this model only deals with 3 numbers and 4 lines. And you guys are seeing something that only 3% of doctors could grasp when they were dealing just with dry formulas and abstract propositions. Okay, on we go.
All right, so hold on. Where was question 2? I don't remember when we do that. Actually, go ahead. Yeah, just go forward.
Question two is the very next slide.
All right, go ahead and go forward. All right, so we're going to find the area of each rectangle. So if you wanted to find the areas of these rectangles, you just multiply length times width, right? So the 1% times the 90%. Keep going, Dad. For the false negatives, the 10% of that side times the 1%. So again, length times width of each one. Keep going. False positive, 99% times 10%. Keep going. And then true negatives, 99% times 90%. That's what you guys already did with the tree, right? It's the same exact numbers. So go ahead and go to the next slide, Dad. What I'd like you guys to do for question 2 now is answer question 2. You guys are finding what's the conditional probability, okay? So given your patient has a positive mammogram, what is the conditional probability that they actually have cancer? Go ahead and we're only talking about the people who actually got that positive test. So the worry is when you get that positive test, what do people immediately think actually when they get it? Patrick? Oh, that they have cancer, that they're going to die, all these things, right? And this is where doctors need to be a little bit more careful about that. So probability of cancer, given they got the positive test, go ahead, Dad. Who has a positive test? Which 2 groups actually had positives here? And you can just say the labels. Francisco?
The false positives and the true positives?
The false positives and the true positives. Those were our positive tests, right? So that's going to be our denominator. That's all the group that we're looking at. Okay, go ahead, Dad. So that's those 2 groups there. Your denominator should be, again, ahead. All right. Adding those 2 up for your denominator. One more slide, one more. And then the numerator is the people who were actually positive out of that group. It was only 0.9%. Those were the true positives. What is this result when you get 8.3%? What's that result telling us? Why is that kind of important? Liam?
That's like it's like accurate in like a large sense, but it's not super accurate.
Okay. That's true. There's some problems with accuracy in this test. Hannah?
With only 8% that is actually positive.
Right. So again, don't freak out. You need to do the next test to see to go on, right? It's not like you have cancer if you got a positive mammogram. You only have an 8.3% chance of that actually being the case. Go ahead and go to the next slide, Dad. And just a little time check. We got 15 minutes left, okay?
Okay. So I want to emphasize that this is valuable information. You're surprised at how low the predictive value is, but as a doctor, I have something to work with. The patient in front of me has 8 times greater chance of having breast cancer than the general population. This has helped me tremendously. And guess what? It's helped the patient. Yeah, she's going to worry, and we're going to take action and resolve and hope that she's in the 92% that don't have cancer. But lives were saved. Lives were saved. The investment of doing this mammogram and worrying a lot of people actually saved lives. And we'll see when we get to COVID that that's true as well.
And then just a quick comment. This was in your last night's article. The positive predictive value is that number that we're looking at, that conditional probability. All right, go ahead, Dad.
I'll say on to COVID. You worked with these numbers already, so these are familiar. And now you're going to do the conditional probability for this and figure out the likelihood of false alarm.
All right, so we're going to do another question here. It's the third question, okay? And I'm going to give you guys 5 minutes for this. You're going to use a couple of assumptions, right? We're already assuming that the sensitivity is 95% for a PCR test for COVID, and that the specificity is 98%. There's actually a Desmos E tool, so you don't have to like do all these calculations on your own or make a tree or make a diagram. So if you log into today's agenda, and if you want to just do it with the person next to you, or everyone wants to get out their computer, I'll leave it up to you. It's linked into today's agenda. You'll be able to actually adjust these. What I'd like you to do at your table is split these up. Someone take 10%, someone take 3%, someone take 1%. And if you have a fourth person at your table, someone take 0.1%. Prevalence, that means how many people actually have COVID currently, okay? So let's take 5 minutes and work on that. Put stuff away, and then you go have a chance to closure, okay? Go ahead and take a look at this table. So this is what, as a team, you should have put together. If you didn't get other ones, go ahead and copy some of these values down, and then Dad, you can go ahead and start talking about it.
Okay, so for our family, the most important row in this table is the 3% row, because that was the background prevalence of COVID in San Mateo on September 11th, when my grandson and Tim's nephew tested positive. Okay. And this is data in a fast-moving pandemic. Remember, the sensitivity and specificity. These numbers were collected at Disney from September through December in 2020. And our family case was from 2 months ago. Just bear that in mind. Now, let's look at prevalence today in Yolo County.
Actually, Dad, can we go backwards a second? Can we look at that table again just to kind of let it all sink in? So just looking at the data that's here, can someone just kind of explain to me what's going on as you look at the prevalence of the disease in the community? And then you look at actually the positive predictive value. What's happening as the prevalence of the disease goes down? Let's go here to Zach.
Positive predictive predictive value also goes down.
Okay, so what does that practically mean? So prevalence goes down, positive predictive value goes down of the test. What does that practically mean for the community? Yes?
I think for if the PPV is lower, that means that the chances that you get a positive result and it's true is less likely.
Yeah, so the idea here is that as that prevalence goes down, the likelihood that your positive is accidentally a false positive goes up, okay? So the actual predictive value goes down and you're a little bit more likely to have had a false positive. Now, there are some caveats to that. I don't want you to take away from this that COVID tests are inaccurate. No, we're going to talk about that a little bit and talk about what we should consider as well. So, Dad, go ahead and continue.
Okay, so as I said, the data we're dealing with is old, right? From Disney, it's from almost a year ago. And our family case was from 2 months ago. So just bear that in mind. The sensitivity and the specificity at those times may have been slightly different than what they are now in Yolo County. And the prevalence in Yolo County is about 1%. This is from the New York Times. They keep track of all 3,000 counties in America, and with their data crunching staff, keep it up to date. And that's how we found out in September it was 3% in San Mateo. And so it's not a pure prevalence in the screening sense, because this is pooled results from all the labs in Yolo County. And sure, some of those tests are done for screening in the school situation, for instance. But some of those tests come to a lab from a doctor who's dealing with a patient that has symptoms. And that is no longer screening. So it's kind of a contaminated prevalence, but it's the best we got, and it's the proxy that we're going to have to use. And that's the thing. When you're out dealing with a pandemic, you have to make do with the information that you have. You're not in a university where you've set up a very precise experiment to look at how test performance. And so that was as of November 2nd. So that would mean that the positive predictive value was about 32% based on the old numbers. They're old numbers. And 1/3 chance of a true positive, 2/3 chance of a false positive. But the person that does test positive, that's a tremendous amount of information for a doctor. You've gone from having a 1% chance to a 32% chance. And as I talked about with mammograms, that woman who has a positive mammogram has gone from a 1% chance of having breast cancer to an 8% chance. And we're going to act on that. You don't want to walk around with an 8% chance of anything. And so we take it seriously for the sake of the patient. But in COVID, we have to follow every lead we've got to break the contagion. So even if there's only a 1/3 chance of a true positive, we're going to follow all that up. Just like it was worth us to worry about women who tested falsely positive for the screening of breast cancer, it's equally beneficial for us to save lives by running down every body that has a 1/3 chance of having COVID. So Tim, I think you were going to talk about some assumptions.
Yeah, go ahead and just click on the next thing. So we made a bunch of assumptions in data. So we assume that the prevalence is correct, right? That it's 1% in our community in Yolo County currently. Again, that's a proxy. We only have the information that we have. We don't know. We're not God. We can't know who exactly has and how many people exactly have COVID. We can't know that for sure at any one moment, right? So that's an assumption that we're making, that is as good as we can get with that. Go ahead and click the next one, Dad. We're also assuming that the sensitivity and the specificity of the disease are 95 and 98%. So I wanted to just show real quick, Dad, I'm gonna share my screen. So if we change the assumptions about sensitivity and specificity, which very possibly they could be higher. In fact, my dad and I have had a conversation with another doctor friend of mine who he thinks that they're probably actually higher than 95% and 98%. But we're going based on what we were able to find online, which isn't, to be honest, a lot of information quite yet, or good studies about the sensitivity and specificity. But if we would change those assumptions, can anybody tell me, like, again, this is where Yolo County is, 32% positive predictive value. So anybody want to tell me something I can change in terms of sensitivity and specificity? How can I change that so that this PPV actually goes up? What could I do with the sensitivity and specificity? Anybody want to give it a shot as to which one of those might make a bigger effect? Egg, what do you think? So we could change the prevalence. Yeah, let's say if the prevalence is much higher, right, at 10%, all of a sudden our positive predictive value is much higher. So as the prevalence changes, and this is why when COVID is raging in the community, you got to be way more careful because, again, although there's very little false positives at that point. Most of your positives are true positives. Let's say the prevalence stays at 1%. And I want to relax my assumptions on sensitivity or specificity. One of those would actually have a slightly bigger effect on the overall PPV. Django, which one do you think it is?
Sensitivity, because sensitivity is the one that deals with how many true or how accurate your.
Okay, so I'm going to go ahead and do that. I'm going to change the sensitivity up here to 100%. As I change that, essentially what's happening is that bottom part is skirting down. But look, did it change very much the actual area of that rectangle? No, so it's actually not sensitivity. I want to minimize in this case, I want to try to minimize which one of these quadrants, true positives, false positives, true negatives, or false negatives. Calvin.
Well, if specificity is at 100%, and that means that you know everyone who is negative.
Exactly. If specificity is at 100%, I know everyone who is actually negative, and I no longer have any false positives. Okay. So if we changed our assumption, let's say we thought that specificity was like not even 100%, 0.99%. All of a sudden, the PPV is back up to 50%. If it's even higher, 99.5%. It goes up to 2/3. It's kind of switched the other way around. So my only point here is the model is definitely affected, right, by these values. So you make assumptions based on the best data that you can. And it could be that we don't necessarily have all the information we have. So we should take this with a grain of salt, our findings. Does everybody understand that, the general idea? All right.
I'm going to give you the bottom line. You'll discover that you verified that as the prevalence goes down, the positive predictive value also goes down. This was of interest to our family because Mr. Lee's nephew, Iko, and my grandson tested positive in San Mateo school when San Mateo was at 3%. And I pulled out my model and I said, hold on, everybody. It's not 100%. It's going to be somewhere between 40 and 70%. And we'll go on to the next slide. What's the prevalence? It was 3% in San Mateo. In Yolo County, it's 1% now. The New York Times provides that. And so that'll help you. I think we can skip some of these. This is what I wanted to be sure we got to, because if you test positive, oh my goodness, what do we do? Well, the next test, this is the gold standard test. You just repeat the same test after 24 hours. Now, our grandson, after he waited 24 hours, was tested again. It was negative. Oh, now we have a jump ball. Okay, 2 out of 3 wins. And you do the test a third time, and it was negative. And all this algorithm was developed by Disney as they were making movies on the set. They could afford to do this, and they had the machines there. And okay, yeah, so positive, and we know that it's the gold standard, so we simply repeat it. And if it's negative, it's a jump ball in a third time, and this was the Disney algorithm. Okay, takeaways from COVID. It's really a tough pandemic because there's a lot of asymptomatic carriers. So it's really important. Every lead that we get, we follow it up. And you know the prevalence matters a lot. No test is perfect. And Mr. Lee has made this point. The vaccines are a godsend. They lower the stakes. It's no longer as much about death or hospitalization. And I want to go back to the mammogram screening and take you back and just review one more refinement. So you remember you did this calculation and you came up with 8.3. And stuck here. Okay, there it is. You came up with the 8.3 in your calculations, but watch what happens to the 8.3 now as we realize, hey, I've got a positive mammogram. What's my next step? There's a follow-up step. There's a second test. I can do an ultrasound. If that's just a bag of fluid that's causing an abnormal mammogram, that's great. So now I'm going to add a second test serially on top of the first test, and it's got a sensitivity and specificity of its own. So we take out Mr. Lee's calculator, and look where the 8.3 is now, the 8.3%.
Can I stop you real quick, Dad? Why did that change from 1% before to now 8.3%? Why do we rethink the prevalence as no longer being 1%, but as being 8.3%? Eleanor.
Because they've already gotten a positive test, so they know that they have some higher chance.
Yes, exactly. So since it wasn't 1%, like 1% was the general population who might have breast cancer. But now that we've gotten a positive test, yeah, 8.3% isn't much, right? It's telling us that actually the mass majority of people are false positives. But now we can do the second test and we know we have, well, there's an 8.3% chance this person actually has it. Because now we're looking at just the people who tested positive for the mammogram. Okay, so that's a perfect explanation. That's now gone up, and now that's changed the probabilities. Even though the sensitivity and specificity are pretty low, they're in the 80s for this, that prevalence being high allows us to get a better idea. Go ahead and finish that.
So what the positive predictive value for the first test becomes the new pre-test probability for the next test. And guess what? You can do serial tests. You can do 3 or 4 tests, and pretty soon, if unfortunately, if this patient has cancer, the prevalence pretest probability line keeps going to the right, increasing the chance that she really has a true positive as opposed to a false positive. Okay, so guess what? This can apply to any bit of information. When we are trying to decide something and whether something's true, we collect information, and each bit of information we add, we usually subconsciously figure in, well, that makes it more probable. Oh, that makes it less probable. But
Sorry, one quick question about the math. If you've gotten new information, the probability of change, is that associated or independent? Associated. Good. All right, continue.
So this way of thinking, one name for it is the Bayes theorem. And what the main point is, your idea of probability should rationally change to account for new information. And if this were true in the political world, we'd be getting along better. People would be changing their opinions. And Bayes, though, didn't call it Bayes' theorem. He called it solving a chances problem. And here he is. He was born over 300 years ago, and he never published. He was a clergyman who was a statistician, mathematician as a hobby. And he never published. When he died, a guy named Price went through his papers and found that he had written an unpublished essay towards the solving a problem of the doctrine of chances. Who was Price? He was a buddy of Benjamin Franklin. Interesting. And so he published then, and he renamed Bayes' essay a method of calculating the exact probability of all conclusions. And by all conclusions, he meant all. He tried to use this way of thinking to argue for the existence of God. All right. Now, what Bayes' great contribution was looking at data in two ways. And that's the 2x2 table. He took some data and with different variables, and he just figured out you could look at the data vertically, and then you can look at it horizontally, which is exactly what we've been doing with the 2x2 table. That's his great insight. It has many different names. If I'm going to rename my little project, I'm going to call it this. Mathematically, it looks like this.